Of the best practice of the profiling tools on Blue Waters. I more talk about general feature of the gray path. But as Greg said, we cannot talk about all of them. So I will just try to deliver a couple of nuggets, maybe useful for you. So intentionally, I made this PowerPoint file very intensive, but it doesn't mean I need to do everything. So as Galen said, it will be uploaded to Blue Water portal, so you can read it later. So I will just tell you something important. So okay. So everyone knows Blue Water, so I'll skip that. And basically, CrayPad is a Cray native profiling tool. So if you want to know some performance metric, you can use some Intel profiler or some, but the Cray native profiler is CrayPad. So you can do some automatic profiling analysis and you can check load imbalance. But it's a great tool, but there are several limitations. One of the limitations is CrayPad instrument the executable binary. So if you don't have executable binary, you cannot use CrayPad. For example, if you are using Python, and if you run with Python wrapper, you don't have any explicit executable binary, so CrayPad does not understand what it is. Cray understand the Python is the cool tool for new generation of the HPC community, so they are working on it, but at the moment it doesn't work. The another thing is CrayPad we can do the tracing or we can do the sampling with the CrayPad. But if you use the tracing with CrayPad, you had better use some limited number of the MPI rank. The reason is tracing make a lot of raw data for the profiling, from the profiling. So if you do the tracing for half-scale Blue Waters, you will have really huge data and you cannot open that. So yeah, that is kind of the limitation of the CrayPad. But if you use the sampling, you can get quite decent size of the raw data and you can see a lot of details. There are two modes of the use, CrayPad Lite and CrayPad. So it is, Cray updated these two modes from last year. So if you're a novice user of CrayPad, you may try CrayPad Lite. Or if you want to use some in-depth profiling, you can use CrayPad traditional way. So in order to use CrayPad, first of all, you need to unload Darshan because it has conflict. After that, you need to load CrayPad perp tool space and perp tool Lite for the CrayPad Lite. Or if you want to use CrayPad, you can load perp tool base and perp tools. And this blue box shows currently available CrayPad module on Blue Waters. You can choose one of them. And several users ask us, say they cannot use CrayPad because they don't use Cray compiler, but it's not true. So you can use any compiler on Blue Water with CrayPad. Most of the function is available with other older compilers, but there are some limitations. So if you want to use Reveal, which is OpenMP threading advisor by Cray, you have to use Cray compiler. Or if you want to do some root work estimate, or if you want to do some tracing for UPC or core array Fortran, you have to use Cray compiler. Other than that, you can use CrayPad for other options. Procedure. You need to update your module for CrayPad, so loading Darshan, loading perp tool base and perp tools. And then you need to build your program again. And you don't need to add any special flag. -G is required for the debugging, but for profiling, you don't need to do that. Or you can use any optimization flag. There are several ways to instrument your original program, like presented here. But if you just do the path build and your original program, you will get the default the instrumented binary with the default version. Default version is automatic profiling analysis. And if you want to use the CrayPad API, I will discuss it later. You have to use a path build -w and your original program name, or you can choose any other options. So After running this pet build, you will have another binary, instrumented binary, ended with plus pet. So for profiling, you need to run plus pet executable without instead of your original program. So for running, it's simple. Just do the app run and use your plus pet executable file. If after running this one, you will get some file, .xf file ended with S or T. So S means this XF file is from the sampling, and the T ended with T. This file is for tracing. So you can get one of them. And there are many CRAPAD runtime environments, but I will just introduce two of them. One is CRAPAD do the profiling in detail, but for the report, they just accumulate the data and they try to reduce the size of the raw data, profiling data. But that is default. But if you don't like that, you want to see more data than that, you can set pet RT summary is equal to 0, and then you can get all the detailed profile data. Another thing is pet RT perp CTR. This is perp CTR. This is sometimes if you want to do some memory cache, you want to check some cache utilization, you have to use some hardware monitor from your CPU or network. So in that case, you can select a set of hardware counter using pet RT perp CTR, and I will discuss it later. Okay, so after setting the runtime environment, and if you run it, you will get the XF file, and then you need to process you need to create the report using pet report. So pet report and .xf file, and then you will have a AP2 file, which is info file of your Cray Apprentice 2. This is GUI-based report pet profiling viewer. Or you may just see the text-based result using the AP2 file. So Galen briefly showed how it looks, the Cray Apprentice 2, how it looks. So I will just skip that. Okay, CRAPAD API. So most of us are working on the production level legacy code. So as Galen said, your code is really long. So someday you improve your program by updating some corners. So it is very small part, and after updating this corner, you may just want to look at what is performance of that updated kernel. For this aspect, CRAPAD API is really crucial to use that. So you can turning data capture on and off at the key point, and for that you need to insert the API call to your source file. So first of all, you need to add header file for C language and Fortran language, depending on what is your primary language. And you may use a compiler macro cray_pad. So sometimes you use a cray machine, it doesn't matter, but sometimes you don't use cray machine. In that case, you don't want to update your source code. So if you use a cray compiler macro, you can activate it, deactivate easily when you build your program, even after including your CRAPAD API calls. There are many API calls, but I will just mention about 3 of them. First one is pet record. This is you are telling you from this point start profiling, and then if you put the pet state on, your program start profiling from that point, and you can set you can add the pet record with this pet state off, and you can stop the profiling. Between the record on and record off, you can add several pet region to see the profiling data. So for that, you can use pet region begin and pet region end. So you may set several regions, but in that case, the pet regions should be either separate or nested. It cannot be overlap each other. At the bottom, you can see the example. So I set the pet record on the first line, and then I set up the 2 pet region 1 and pet region 2, and then I put the pet record off. I will show you some example about how to profile them with regard to memory. So I believe everybody knows the L1, L2, L3 cache and the DDR memory. So I will skip this one. This slide is about the PAD RT perp CTR. This is to select your hardware counter. Basically, the AMD Interago process has 4 hardware counter, so you can choose up to 4. And if you want to know more details, you can after updating your module for the cray path or loading version and loading perp tool base and perp tools. And then if you run the PAD help counters AMD FAM 15H, you can see the hardware counter for your AMD process. And there are 4 groups, drive groups, native, and PAPI. PAPI is a performance counter by PAPI, and there are several examples at the bottom. So PAPI L1 DCA, this is for the data cache access, and PAPI FE OPS, this is floating point operation. So if you want to know what is the number of floating operation, you can include this one to PEP RT perp CTL. Okay, another group is native. Native is the AMD native performance counter. So this is one of examples. If you want to see some L3 cache miss, you can choose this Cray MB L3 cache miss, and it has several subgroups, and you can also choose one of them. And another group is drive metric, which called drive. This is computed from the PAPI counter and AMD native counter. So, for example, if you want to know what is D1, D2 cache ratio, it will compute using this equation. Or if you are interested in computation intensity, for example, for loop line analysis, x-axis is computation intensity. So if you choose that, you can also get that data. But there are very many counters here, but I recommend you start with the group predefined counters group. So there are many groups from ID 0 to 23 with some lost numbers, and there are several examples. For example, if you want to know what is L1 cache, L2 cache matrix, you can just choose group 2, and then it will call the PAPI L1 DCA and PAPI L DCM and etc. Or if you want to know the data cache utilization with the floating point operation, you can choose group number 23, and you can get that data. Okay, so I will show you 2 very simple examples how to use CrayPad. First example is a toy problem. Just want to compute the square of the 2D array in Fortran. For that, first of all, I added the headers for Fortran in my source code with the Cray compiler macro. And then I added path regions. So, okay. So here I set the path record on, and here I set the path record up. And these 5 lines are main kernel. I wanna get the performance data. And I set the path region 1 here, start, end, begin, and I set the path region end here. And then I instrument the executable binary. So the binary name is SQU array MPI plus 03. So I do the path build -w and executable file name. And then I ran the instrumented executable. So this is under interactive bash mode, and you can also do the JavaScript. So first of all, I set my hardware counter. So I export path RT perp tool CTR is equal to 2 because I want to know what is L1 and L2 metric. And then I ran the app run with the instrumented executable. So it ran, and then it create this SQU array MPI03 plus path and number t.xf file, which means XF file has some trace, the data from tracing. And then I created the report using path report and putting the XF file. Yes.
One thing quick about if you haven't used the PAT report tools, JaeHyuk has shown a good example here. Immediately once he gets the .xf file, then he's immediately runs pat report to get the .ap2 file. It's really best, even if you're not going to look at the profiling data right away, to run the pat report right then, because the xf file is tied specifically to the executable that you built. So if you rebuild the code and run another sampling, your data's gone. So the .ap2 file is forever. That contains all the reference information inside of it. You can look at it 6 months from now and it's fine. The .xf is referenced specifically to the executable that it was run under. So you should really run that right away, and then later you can pull whatever data, including the summary that it spits out afterwards.
Yes, as Craig said, it's possibility to lose XF file because XF file has path binary number, but it has some PID and node ID, but still there is possibility to lose this data because if you use same node ID and it may be overwritten, right?
But if you rebuild the executable, you can't extract the AP2 later. It's specifically referenced to the executable that it was instrumented against.
Okay. Yeah. So do pad report just after running. Okay. Okay. Good. Okay. So after running Efron and do the pad report immediately, you will get the big text file, and this is part of that. So I set the region 1 as AIJ square. So I set it here. I just named. This region ID is 1, and I just named it like this way. And you can find it out, this block. There are many data because I selected group 2. And most important thing is D1 cache hit is 0%. It's really bad. And D1 plus D2 cache hit is just 36%. It's really poor. So something going wrong. And average time of this kernel is kind of 0.13 seconds. So without this data, we don't know this is optimized or not. But after running the Cray pad, we know okay something going wrong because my D1 cache hit ratio is 0, D1 D2 cache hit ratio is just 36%. And if you look back to our source code. We can realize that this is not stride 1 reference pattern because Fortran is column-based array, so you have to have the first index at the inner loop. So I just swapped the I and j, and then I ran it again. And what happened is, okay, D1 cache hit is 89%, which is not great, but much better than before. And D1 plus D2 cache hit ratio is 95%. It's not great. So usually we say if you have the D1 cache hit ratio is more than 90%, this is good. And D1, D2 cache hit ratio should be at least 97%. But it's a little bit lower than that, but still much better than before. And the runtime become 0.05 seconds, so much faster than previous one. So this is a very simple toy problem, how to use GrayPad. And the second one is I needed to run some HPC benchmark, which is called HPGMG. And it runs 3 different resolution of mesh. So I want to know what is flop rates of each resolution of mesh. So for that, I use GrayPad. So this is written in C. And I added the header for C here and add region. So I started record at here, so record on and record off. And the kernel I'm interested in was just these 2 lines, so restriction and the bench HPGMG. And I set the 3 different path regions looks overlapped, but actually this is 2 loops, so they are separate each other. So I set the 3 regions. One is for 1H resolution, second one is 2H, third one is 4H resolution. And then I did I create the instrumented executable using the path build -w HPGMG, and then for runtime now I want to know what is the flop rate. Okay, so flop rate. So I set group 23, including floating operation number, and I ran with 1024 MPI rank. So this is part of the CRAPAD report. It gives us a percentage of the world time of a specific region, and it also gives us what is high memory high watermark. So what is the maximum usage of memory? And then I looked at the regions for 1H, and I see the D1, D2 cache ratio is 99%. It's really well written code. And the flop rate is 1.1 teraflop per second, and computation intensity is 0.89. And I keep doing to 2H, and very good cache utilization, and flop rate is a little bit lower than that. And 4, 99% cache utilization, and the flop rate is 800 gigaflops. So after doing profiling several cases, I could see all of cases, the D1, D2 cache ratio is really high, almost 99%. It's really well written code, so good for benchmark. And what happened is, this is kind of the part of the loop line analysis. So loop line analysis, you have the computation intensity on x-axis, and your performance could be flop rate or the number of equations per second. That is a y-axis. So from this chart, we can see the HBGMG performance is proportional to computation intensity, which means in the loop line analysis, on the left-hand side, you have the inclined loop, which is bounded by memory performance, and on the right-hand side, you have the plateau area, which is bounded by your process performance, right? So from this chart, we can say, HBGMG is memory performance, memory bounded application. So in this case, if you have the HBM in next generation, without any code change, you can bump up your performance with the HBM, high bandwidth memory. Okay, so I just talked about the PAT build, PAT report, and CRAPAD API, and the runtime environment, PAT RT purpose ETL. Any question?